hydrocarbons that are single bonded everywhere. And the term we use for that is alkane, and there's another word for as many hydrogens as you could possibly get on it. We talked about fats. Saturated, right? So we call that saturated. Okay, so now what we're going to do is we're going to work on naming these things. So one of the tricks in naming is you have to always find the longest chain. So this one, and one of the tricks in naming is that your teacher will never give you the longest chain as the straight chain across the middle. So what you have to do is you have to look at a structure and say, what's the longest chain? And you might have to count like 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 4, 5, 6, 7. So you have to go through that whole thing. This is the longest chain for this particular compound. So we count 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9 in the longest chain, and so automatically this becomes a no-name. Why is it a no-name, not a no-name? It's 9, yeah. So if you look over here, there's 9 is known, and then you just add the A-N-E to the end of it, and that gives you no name. Very good. Okay, so they say smart to memorize 1 to 10. I say smart to memorize 1 through more than 10. Go to about 15. And then after that, it's all systematic. You can just remember it. Like 30 is try. Right, so just to show you back here, go back one slide. This is triacont, and this is icos. Once you memorize how you can go from 10 to 11 through 15, basically you apply the same logic to 20, 30, 40, 50. You won't have to name anything that long. So try to get up to 15 and you'll be good. Now, so here's this compound. And you'll notice in this particular compound, there are 2 chains that are exactly the same length. There's 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. When we do the naming, what we do is we name the parent chain. That's the first thing. And the second thing we do is we name the substituents, okay? But a substituent is anything hanging off the parent chain. So this is hanging off the parent chain, this is hanging off the parent chain, right? That's hanging off the parent chain, that is, and that is. The rule that we use for determining which one could be the parent when there's a tie is the one that generates the most substituents. So that would be the one on the left. The reasoning for that is that if you have more substituents, they will have simpler names. Okay? It turns out it's going to be easier to name these as substituents rather than naming that as a substituent there. Although that has a name too as a substituent. You'll see sometimes you're just going to name that. So this is a no-name. Oh, sorry, what did I count it again? 1, 2, 3, 4, 5, 6, 7. Yeah, heptane, sorry. I had no-name on my brain. Maybe I skipped a bunch of slides. Oh yeah, I did. So let me go on and explain a little bit more how you do the naming. Gotta get my pen out. I'm gonna zoom in. There we go. So that's 1 carbon, right? So mother eats peanut butter. What's 1 carbon? Meth, right? So this is known as if it was an alkane, it would be methane, but as a substituent, we will say methyl, like M. So that'll be a methyl substituent. Now you'll notice there's 2 of these substituents, right? What are those? Ethyl, right? So it would, as an alkane, it'd be ethane. As a substituent, it ends in the YL. So this is ethyl. Oops. Now, one of the things that you have to do with the parent chain, so once you identify the substituents, you have to number the chain. Okay? The numbering of the chain always goes so that the first substituent has the lowest possible number. So let me draw this again. I'm going to draw it on a new slide. Whoa, I don't want that. Sample custom. Like all my slides disappeared. Let's just do that. Oh, no, that's just a custom background. No, okay, good. And let's wipe that. So I had 7. Oh, gosh. You know what I better do is go back and look at that. Yeah, I'll just do it from here. I'm going to call this the number 1 carbon that's down here. The other option is to call this the number 1 carbon. All right? Because you're going to count. But in this case, because I go 1, 2, 3, 4, 5, 6, 7, this first substituent gets the lowest possible number. So that's why I start numbering from this end. So that one, we don't do. Now, when you put the name together, so you first thing you do, parent chain. Second thing you do is number the parent chain, okay? Third thing you do is you have names for all the substituents. Now, I named them all already. The fourth thing you do is you just put the name together. Okay, so how do you put the name together? You do all the substituents alphabetically and you indicate where they are on the parent chain. So, trying to find a good space on this slide to write. I'll write over here. So I have a methyl. What position is the methyl in? In the 2 position, right? So that would be a 2-methyl, like that. Okay? Now, the ethyls are in 2 different positions, right? Which carbons are they on? 3 and 4. So what you would do is you would say 3, 4. And because there's 2 of them, you indicate how many they are by a prefix. So mono, di, tri, tetra, penta, those prefixes that you've used before. This would be diethyl. Okay? And then you get to put the whole thing together. Now, for the purposes of alphabetizing the name, you don't use this di prefix. You're only going to use the M and the E. So if you're like me, whenever I alphabetize things in the back of my head, I'm always singing A, B, C, D, E, F, G, H, I, J, K, L, M, N, P. So what comes first? What's that? The 3, 4 diethyl, right? So to name this, I would say 3, 4 diethyl hyphen, right? 2-methyl and how many, what's the parent chain?
Heptane.
Heptane. So those are generally the rules for naming a alkane. There's some details we'll get into as we go through the slides. And there's more examples and stuff that come later. I wanted to say something else about this. What was it I wanted to say? Oh yeah. Now you know why common names are so common. This is a very small molecule, and that's the name. When you get to like 10 or 20 carbons with multiple substituents, the names get unreadable, so they get names like heparin, right? Those names would be so large if they were systematic that nobody would ever know what they were when they gave them to you, and every time it was published in a paper, it would take up half the page. So then they give it a common name. So a lot of drugs that you see get common names just because nobody wants to go through the bother of trying to name systematically what that thing is. Even though they have those. There's computer programs that will generate these names. That program that I told you to download for drawing, should generate names for structures. So if you draw a structure, you want to test yourself, you just draw yourself a structure and then you name it, and then you have the program generate the name just to see how you did. Okay, in addition to alkanes that are straight chains, we have alkanes that are cyclic. Those are closed chains, okay? So we have cyclopropane, cyclobutane, and cyclopentane. Again, cyclopropane is the smallest one that you can have. Hey, cyclopropane is the smallest one that you can have. Remember we talked about this in a previous question on the homework about the bond angles, right? The bond angles are 60 degrees, very strained, right? Causes it to be relatively unstable. And then there's cyclobutane, cyclopentane, and also cyclohexane. What would be next? Cycloheptane, cyclooctane, it's the same systematic naming that we use for alkanes, except for we prefix it with cyclo. Any questions? I'm going to show you one other thing about these. Okay. So let's compare cyclobutane to butane in terms of a formula. Okay? So butane would be this. So how many carbons? 4. So it's C4. And then how many hydrogens? 10. It's 2, 4, right? And then 3 and 3 is 6, so 10. H10. Look at cyclobutane. It's C4, right? And then H8. So the way you think about cyclobutane in terms of formula, because it makes a ring, carbons are bonding on themselves. So what happens is, let's say you had a hydrogen here and a hydrogen here, okay? And you got rid of those two and then bonded these two ends together, that would give you cyclobutane. So the general rule is every time you form a ring, you lose 2 hydrogens. Okay? In the formula, it's known as, there's different things, degrees of unsaturation, and what is the other one they call it? Like a hydrogen index number, right? It's always got 2 less hydrogens. So why is that important? When we do constitutional isomers, you're going to have to recognize that if you're missing 2 hydrogens from the alkane, it could have a ring in it. It could also, by the way, be this. A double bond. So the double bond and the ring have the same effect on the formula. You don't know which one it is just from C4H8, because there's 2, right? 3, 4, 5, and then 3 more is 8. Okay. So when you do constitutional isomers, when you're missing a pair of hydrogens, and I give you a formula, there's a lot more formulas that you can have. Because you can have rings with carbons coming off of them. You can have double bonds. Right? Can you have a double bond and a ring?
Yeah.
You can, except it can't be that formula, for example. So let's say I did a double bond. Let's say cyclobutane with a double bond, right? Probably not going to happen, but I think they can make this. It's strained. There's a hydrogen there, right? So 1, 2, 3, 4, 5, 6. So you lose another pair of hydrogens because you put another double bond. That would be known as 2 degrees of unsaturation, and suddenly there's like a lot more formulas that you can have with that structure. Well, with 4 carbons, there's not that many, but if I gave you like 6 carbons and all those degrees of unsaturation, you could just go crazy on a piece of paper forever. And then I could add an oxygen and a nitrogen, and you'd be like killing me. Those are those questions that we write, and then we realize, uh-oh, I shouldn't have given that many options for names. All right, so this is like the textbook slide. I made some modifications. So let's do this. Let's find the parent chain for the compound on the left. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. How many ways can you get to 8? 3. 3, yeah, right? Because if I'm counting, there's starting at this end and ending either here, here, or here, right? It's going to give me 8. So I know the parent, that's the longest chain, is going to be an octane, okay? What's the path that I'm going to take? Let's call them like this, A, B, or C.
Not C. B.
B?
Or A or B is the same.
Or A. Yeah, either one is the same. This is a rotation, right? So I could either go A or B. It's not C. Not C because when you go through C, even though you get 8, you've got this crazy side chain here and another branch coming off of it. So remember, the rule is you want the most possible substituents. And so when you number this one, you're going to number it along this long chain here or here. Which end are you going to number it from?
A or B end.
You're going to number it from the A or B end. So I'm going to call this 1 down here. This is 2, 3, 4, 5, 6, 7, and 8. And get rid of that up there. Okay. So that's the parent chain. We'll name that one later. But the first thing is we got to recognize the parent chain. So what's the parent chain here? On the right. Trick question. It's drawn to make you say that. It's drawn to make you go like from here all the way up to here. But the parent has to be either a chain or a ring, and it can't be carbons in both, right? So you can't go 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the parent name may not include carbons that are both in a ring and outside a ring. So you can't count through a ring and get to the other side, in other words. So in this case, 1, 2, 3, 4, this is what you have here, but in the ring you have, looks like 7. 1, 2, 3, 4, 5, 6, 7. So the parent for the one on the right is a cycloheptane. Yeah? The numbering is going to be a little funny, but we'll get to that. Because ring numbering is funny because like that could be 1 or that could be 1, and you can go 1, 2, 3 this way, or you can go 1, 2, 3 that way. Right? You can count in different directions. So we'll talk about that when we get there. Okay. This is, I will skip this. This is the thing about substituents that I talked about earlier. But this is just to quickly review. You find the parent chain. Sometimes actually it helps to redraw the parent chain so that it's straight. Because I'm not going to give it to you straight. I'm going to give it to you all crooked and zigzagged on top of itself. Because you know why you do that? Because that's the way it was done to me. Pretty much, you know what? Never mind. I was going to say something inappropriate perhaps, but yeah. So yeah, in this case, it sometimes helps to draw it straight. These would be the substituents. They're the same as the terms from table 4.2 in your book. Instead of ending in A, you end them in YL, and then you have your substituents names. Okay, so ring or chain. So in the case on the left, when you identify the parent, okay, there's this sort of general, it's actually written, IUPAC, the organization, International Union of Pure and Applied Chemistry, has this thing called the Blue Book, okay? And the Blue Book lists the organic nomenclature rules. And so if you want a copy of it, I can probably get you a copy. It's many hundreds of megabytes long, I think. It's hundreds of pages of rules. Okay, we do the simplest, and they have suggested rules. Like, they're not absolute, but these are suggested rules. The thing about rings and chains is one of these rules that they have that's a kind of a suggested rule. So you notice here, the parent is the ring, right? But the reason the parent's the ring is because if you count the ring, it's got 6, and then the chain has 3, so it's a substituent. In this case, the parent has 4, and the substituent would then be the 3. So whichever one's longer is generally the parent, and whichever one's shorter is generally the substituent, unless you invoke the rule that says the ring is always the parent. Don't do that. We're not going to do that. Okay? The only time that we're going to do that is when you get a situation that looks like this. So longer chain, longer number of carbons, parent. That's simple. When it's a tie, it goes to the ring. So if I have, and I'm just doing this for the sake of brevity, 3 and 3, right? Just call that the parent. And then the other thing is the substituent, okay? So that's the rule we'll stick with. Although it's kind of ambiguous at that point. You can do either one. All right, so we're going to name these substituents. We'll start with the one on the left. That's my octane, right? So let's start by naming, I called this 1, right? So we're going to name this, and this, and this, because those are all 1 carbon, right? So those will be methyls. And then I'm going to do that. And that's an ethyl. Now I'm numbering the chain from the bottom right to give the most number of substituents. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. And we talked about this already. It's an octane. But I have how many methyl groups? 3. So it's going to be 2, 3, 6 trimethyl. Okay. So I'm going to add the 2, 3, 6 trimethyl. Again, for alphabetization, we use the M, not the T. Otherwise, they would shift all over the place all the time. And then on 3, I have ethyl. So this thing, when you name it, what comes first? Ethyl. 3, ethyl. 2, 3, 6. Trimethyl. And then octane. Okay. So alphabetically, we decided this is 1, 2, 3, 4, right? Butyl. And these are ethyls, right? So what comes first? Okay. So what you do when you, this is the weird thing about a ring, is what you're going to do is when you name, or when you number the parent chain, the first letter comes first. Alphabetically, whichever one is the lowest gets the preference. That is, it gets the number 1 position in terms of its priority of where it goes. So, in other words, this is a butyl. These are ethyls. Yeah, that's nasty handwriting, huh? It's funny, like at different zoom levels, it writes all differently for me. I don't can't quite get the hang of that. I have not had any ethyl today. All right. So this is 1, 2, 3, 4, 5, 6, 7. So that way, since butyl is going to come first alphabetically, go ahead.
Does it matter if you go counterclockwise or clockwise? Or?
Yeah, it does, because you want to give the substituents the lowest possible set of numbers. So if I start with this as a 1, okay, and I go here and call this 2, then all of a sudden these become 6 and 7. 3 and 2 will become 6 and 7. So we don't go that way. We go in the direction that gives us the lowest set of numbers. And it doesn't matter if I start here and go this way or start here and go that way. So how would you name that?
You have to add the one.
What's that?
You have to put the one.
One view.
One
Oh,
line.
yeah. So, yeah, 1 butyl, right? A lot of people will say you can leave that off hand because it's implied that it's in the number 1 position because it's on a ring. So you can leave it off. The reality is, most of the time people will leave it in there. Okay, so I don't care either way with the number 1. So you leave it or not. I think technically you take it off. So this will be 1 butyl. Oops. Maybe if I zoom in and 2,3 diethyl. And then, yes, cycloheptane. It would have been so easy to have windows in this room, but they didn't put them in. Sorry. I just recorded that. Okay, so here's a situation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Doesn't matter which way I number it. But this substituent will never give you a longer chain, so you have to name that. Okay. So what do you do when you have a quote-unquote complicated substituent? First of all, wherever it attaches, that's the number 1 for the side chain. Okay. What you're going to do is you're going to number the parent chain. In this case, it'll be 6, and it's an undecane, right? Because it's 11. I counted 11, right? I forgot already. And then this is going to be number 1, 2, 3, 4. Okay. We will number it from here. Trying to see what's on the next slide because it might actually give us more. Yeah. So in reality, what we're going to do is we're going to number this side chain from this position here. And it's going to get its own set of numbers. And the reason I have to do that is because it's on the number 2 carbon of the side chain. It's got its own side chain. Right? So this is a 2-methyl group on the side chain. So all the rules that you applied, okay, for the parent chain, for giving substituents names, you apply those rules to the side chains, except for when you indicate this is the 6, right? You're going to indicate that this is 6, and this will be a 2-methyl butyl group, and doesn't end in a butane like a regular alkane would end in ane. So whatever you do to name this parent chain and its substituents, you apply those same rules to the side chains. Okay, so number the longest chain within the substituent. Start numbering from where it's attached to the chain, the parent chain. So this substituent name, just by itself, is 2-methyl butyl. This is what we talked about. And again, the 1 is not necessary, so it's left out. But sometimes people put it in and it's not the end of the world. It's just extra information. Now, what do you do with this? 2-methyl butyl. Where's it at? It's on the 6 carbon of the undecane, right? So now when you do this whole name, I'm not going to write it all out. I'm going to cheat. I'm going to zoom in and make it really small. It's going to be 6, 6 hyphen, and then in parentheses, 2-methyl butyl. That's to indicate that this is attached at the 6th position of the next thing that's named. Okay? Undecane. But again, it's systematic nomenclature, so everything you do for a parent chain, you do for a side chain as well. The only difference is in the side chain, you always number 1 the carbon where it's attached, or the atom where it's attached, and the carbon attached to that atom would be the number 1 position. Oh, okay. Well, so one of the things that we teach you about systematic nomenclature is that if you give it a name, right, it's unique. So there are some structures in organic chemistry that have been around for so long that they've been naming as different things, is they have their own different names. And there's actually more than one way to name a compound sometimes in organic chemistry, okay? So it will still give you a unique compound on the way out, but it's like, actually my kids don't have nicknames. But let's say my son James. Let's say some people called him Jim. Jim or James, this both means the same person, right? So that's basically what this is. Isopropyl and 1-methyl ethyl. Now think about what 1-methyl ethyl is. That's the parent is shown as the big blob on the left there. So if you were numbering this chain, you would go 1, 2, right? It's an ethyl group. This is the methyl group. So this would be a 1-methyl ethyl group. Turns out people have for years called this an isopropyl group. So let me show you what the iso groups look like. It is the isomer of propyl side chain. Okay, so isopropyl. Oh wait, let's try this. No, that didn't help. All right, maybe this will work. I'm going to call the rest of the chain R. That's the parent chain. Okay, and I'm going to attach an isobutyl group to it. Now, butyl has 4 carbons, right? So this is isobutyl, 1, 2, 3, 4, and it's branched at the end away from the parent chain. Okay? It's just the one branch, too. So I'm going to do an isopentyl group. I have an R. Isopentyl will have how many carbons? The chain will have how many? 4. Because you're always going to branch just the one carbon. So if pentyl, this is butyl, if this pentyl has 5 carbons in it, the chain's going to be 4 long, and there's going to be a branch of 1 carbon at the end. I think it's the best I've probably ever said that, because usually people just never get this. But the fact that you said "oh" made me feel much better, by the way.
Well, I was counting before it branched off. I was counting up to the point where...
So now I understand. 1, 2, 3, 4. So where's the branch? Here, here, or here? And then right at the end. You don't do it here because then it would just be a pentyl group, right? So 1, 2, 3, 4, and then 1 branch. What about an isooctyl? How many in the parent chain? 7, and the branch will be on the 6th carbon, the second to the last carbon, right? So that an isooctyl, you would just go, here's the R, and then 1, 2, 3, 4, 5, 6, 7, and that would be an isooctyl. Okay, cool. Yeah, there's more. So, oh gosh. Now, different kinds of carbons. I'll give you some of the names for these kinds of carbons that they don't show on here. So, I'm going to draw a structure. Oh, actually, I'm going to change slides by accident. I'm going to draw a structure that looks like this. And I'm going to give each one of these carbons a different kind of name, okay? There's primary carbons. Those are always the carbons at the end of a chain. They're called primaries because they're connected to 1 carbon. Now I have secondary carbons. Okay? How many carbons are the secondaries connected to? 2 carbons. So on that little structure I drew up there, Where's the secondary carbon?
Second from the left.
It's the second to the left. Thank you for clarifying that. And there's also a tertiary carbon, and that's the one in the middle, okay? By the way, the common name for this compound, how many carbons are in there? 1, 2, 3, 4, 5. Isopentane. You'll see this in common names. It's the iso shape, but because it's not attached to anything, it's not a functional group or side chain, right? They just call it isopentane. There's isobutane, there's isooctane, all kinds of isos. Okay, now, so this is called a sec-butyl group. It's a butyl group, but it's not attached to the primary carbon. It's not attached to one of the carbons at the end. It's attached to which carbon?
The first one.
Right. It's attached to this. This is a secondary, and this is a secondary. Right. So in the isofunctional group, in the sec terminology, these are both secondary carbons. If the side chain is attached to a secondary carbon, it's often called sec and then butyl, for example. Now, you notice if you're attached here or here, it's the same. They're both secondary. Okay? You can't do this with a pentane. That is, if I have an R group, let me draw a pentane. And then there's the parent over on this side. Usually we don't use R as the parent, but it's easier than writing parent chain. So that's a secondary, that's a secondary, and that's a secondary. And if you look at this structure, there's actually two types of secondary carbons. There's the one that's in the middle of the entire structure, which is different than these two. So if you use the terminology sec-pentyl, it doesn't mean anything because you can't tell which secondary carbon you're referring to. On a sec-butyl, it's easy to tell because these two are the same and it doesn't matter which one it attaches to, you end up with the same structure. And again, with nomenclature, what you're trying to do is you're trying to get a unique name. So sec-pentyl would not give you a unique name. Now,
So, why is this one secondary?
this one's secondary?
Yeah.
Oh, in terms of the side chain, it's this part here besides the parent is connected to two other carbons.
Okay, so I don't look at the parent.
Yeah, don't look at the parent.
Okay.
Yeah, good point. Don't look at the parent. Just look at what's in the side chain. So now this is isobutyl. This is the one we talked about earlier, right? Isobutyl, butyl's 4, so the longest chain's 3, and it branches 1 from the end, which is actually just right there. So 1, 2, 3, and then there's the branch. So that's isobutyl. Now, there's tert-butyl. What's tert? Tert means it's connected to 3 other carbons, right, other than the parent chain, the parent. And this will be 1, 2, 3, 4. So it's 4 carbons, right? But it's tert because that's the tertiary carbon of the butyl group. Okay? Not counting the thing that it's attached to. Because it turns out the parent, where it's attached to the parent, doesn't have to be a carbon. It could be something else. It could be attached through an oxygen, for example. Okay. I feel like I'm spewing out rules. It's probably because I am. Yeah. Then it gets worse. See this isoamyl. Amyl was the word they used to use for 5 carbon side chains. So this used to be, now they tell you this is isoamyl. This used to be called N-amyl. N is normal. That's the straight chain. 1, 2, 3, 4, 5 chains. So it's pentyl or N-amyl. This is isopentyl or isoamyl. And then this one is called neopentyl. Yeah. Because look at this carbon, it's attached to a carbon, but this carbon, right, 1, 2, 3, 4, 5, is only attached to carbons. There's no hydrogens on it, so they give it the... So what does neo mean? And don't think of like the, the bad, because we all know the other meaning. I hope we do. New, right? It means new. So you have pentyl, right? You have isopentyl, and then, oh my gosh, there's this other new pentyl. That's another pentyl, so this is the neopentyl. Or you could call it as 2,2-dimethylpropyl because it's 1, 2, 3 propyl, right? This is on the 2 carbons, so 2,2-dimethyl propyl, and then whatever the parent chain is attached to. Okay? Oh, goodness. All right, let me, I need to skim through my slides because I compressed a lot of this. This is about numbering the parent chain, but I've kind of been through all this. So let me just skim through these real quick to make sure I haven't missed anything.